Hello everyone, so today we have a really cool question, and over here we're going to be exploring symmetry and a cyclic system of equations. Now, symmetry in general is a very powerful tool, and especially when you have like a cyclic system of equations, especially when they're non-linear, symmetry can really make your life a lot easier, and that's what we're going to see via this question. So this is the problem number 1 from the round 2 of the Polish Mathematical Olympiad in the year 2012. And in this video, we're going to be majorly looking at the cyclic system of equations and how we can solve that. And then obviously exploiting symmetry given in the question or given the equations. And after that, we have some book suggestions for National Math Olympiads. And at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so we need to solve the system of equations given that a, b, c, d are all real numbers. So they are real numbers, they're not integers or natural numbers. So you can have some sort of weird solutions as well, like maybe root 2, root 3, something like that. So the first thing that I can just notice is maybe if I just like label these as 1, 2, let me just write it out. So I have a cube plus b is equal to c. I have b cube plus c is equal to d. I have c cube plus d is equal to a. And I have d cube plus a is equal to b. And the first intuition is that I can just add all four. Now whenever you see like a cyclic system of equation, it's obviously a good idea to add all four together, because somewhere or the other in the solution, there's a very high chance that you will get a good result when you add all of them up, right? And in this scenario, when you add all of them up, you get a cube plus b cube plus c cube plus d cube is equal to 0. Yeah, so I just basically added 1, 2, 3, and 4. So now what does this tell us? This tells us that not all 4 of them can be positive, or not all 4 of them can be negative. Because if all 4 of them are positive, then this thing on the left hand side will be greater than 0. Similarly, if all 4 are negative, the left hand side will be less than 0. It cannot be 0. So therefore, a, b, c, d, some must be positive and some must be negative. We don't know which are positive, which are negative. So let's just maybe like divide this into two cases. Case 1 where a is positive and case 2 a is negative. And then let's just explore the signs of B, C, and D. So for this case that a is positive, if maybe we can consider b greater than 0, then from equation number 1, what was that? A cube plus b is equal to c. A is positive, b is positive, so therefore c also has to be positive. And from equation maybe number, maybe let's take another equation, maybe let's just take b cube plus c is equal to d, right? So again, b is greater than 0, right? C is greater than 0. So obviously d has to be greater than 0. So here what we are getting, we are assuming a greater than 0, b greater than 0. And as a consequence of that, we are getting c and d also as positive numbers. This cannot happen. So this is a contradiction. What's the contradiction? That b cannot be greater than 0. So b has to be less than 0, right? So b has to be less than 0 for this case. So if a is positive, then b has to be negative. Now maybe let's just look at equation number 4. Over there, we have d cube plus a is equal to b. So b is less than 0, a is greater than 0, so it's easy to see that d is less than 0 over here. Now, maybe let's just look at equation number 3. And there we have c cube plus d is equal to a. Or in other words, c cube is equal to a minus d. A positive, d negative, so c greater than 0. So here we have a greater than 0, b less than 0, c greater than 0, and d less than 0. Kind of like an alternating pattern. So this is plus, this is minus, this is plus, and this is minus. Now by symmetry, what would be the case too? Negative, positive, negative, positive. Purely via symmetry. You can try this on your own if you're a little bit uncomfortable with the exercise, but we can see very well by symmetry that will be like this. So basically, a and c have same signs, right? And b and d also have same signs. So we've kind of significantly reduced this problem a little bit, right? Now what I'm going to do is I'm going to take equation number 1 and subtract equation number 3 from it. So what will I get? I'll get a cube plus b minus c cube minus d cube, or minus d is equal to c minus a. So if I just maybe rearrange the terms, I'll get a cube minus c cube plus a minus c is equal to d minus b. And I can just take a minus c as the common term over here. I'll get a square plus ac plus c square plus 1 is equal to d minus b, which is equation number 5. Similarly, what I can do is I can subtract 4 from 2 and I'll get b cube minus d cube plus b minus d is equal to a minus c, and similarly just factorize this. So b minus d, b square plus d square plus bd plus 1, which becomes a minus c, which is equation number 6. Now what I'm going to do is I'm going to make an assumption, right? The assumption is that b minus d is non-zero, and similarly a minus c is non-zero. So effectively b is not d and a is not c. And how does that help me? So when b is not equal to d, I can just divide by b minus d on both sides. So I can just very well write that b square plus bd plus d square plus 1 is equal to a minus c divided by b minus d. Maybe let's just put that as number 7. And similarly from number 5, I can divide by a minus c on both sides. So I'll get a square plus ac plus c square plus 1 as, what will I get? I will get that as d minus b divided by a minus c. So if we can just maybe multiply 7 and 8, so 7 times 8, so I'll get a square plus ac plus c square plus 1 times b square plus bd plus d square plus 1 is equal to negative 1. And well, this I can very clearly see that can never be true, because this is always positive and this is always positive. How are they always positive? Well, a square plus ac plus c square plus 1, all you really need to do is complete the square. Complete the square and life is easy, right? So this becomes a plus c whole square, c by 2 whole square, plus 3 by 4 c square plus 1. And over here, we have b square plus bd plus d square plus 1. And again, completing the square in a similar manner, I get b plus d by 2 whole square plus 3 by 4 d square plus 1. And obviously, guys, both of these things are greater than 0. Can it ever be negative 1? Of course not, right? Both of them are always greater than 0. So therefore, the assumption is incorrect. Assumption that both of these will not be equal to each other is incorrect. Therefore, either a is equal to c or b is equal to d. Right? We have to assume that either. We can't say that both of them are happening. So maybe let's just take case 1, that a is equal to c. Now from equation number 6, what did we have? We had b minus d times b square plus d square plus bd plus 1 is equal to a minus c. Now if a is equal to c, that means that a minus c is 0. This is 0. So obviously this has to be 0, because this thing obviously will never be 0. So therefore b is equal to d. Similarly, if I take case 2, what is case 2? B is equal to d. So b minus d will be 0. And from equation number 5, what did I have over equation number 5? A minus c times a square plus ac plus c square plus 1, that was equal to d minus b. So if this b minus d minus b is 0, and this has to be 0, because obviously this entire expression is never going to be 0. So that means that we have a minus c is equal to 0, which implies a is equal to c. So what are we noticing? You're noticing that if a is equal to c, then automatically b is equal to d as a consequence of that. And similarly, if b is equal to d, then a is equal to c as a consequence of that. Therefore, we have a is equal to c and b is equal to d. So both of them are holding true. And maybe when I just plug this back into our original expression, I can reduce it down a little bit. So I will get a cube plus b is equal to a, and b cube plus a is equal to b. A cube plus b is equal to a, and b cube plus a is equal to b. So effectively, I only have certain expressions, right? I'll get a cube plus b is equal to a. This and this are similar. Similarly, this and this are similar, right? So I only have a cube plus b as a and b cube plus a as b. And again, I just add these expressions. I'll get a cube plus b cube is equal to 0. And this can easily be factorized at a plus b, a square plus b square minus ab is equal to 0. And obviously this has no real solution, so therefore a plus b is equal to 0. So therefore a is equal to minus b. And maybe when I just plug this back into, let's say, this equation, I can just see that b is equal to minus a. So I'll get a cube minus a is equal to a, or a cube is equal to 2a, or I can just say that a cube minus 2a is equal to 0. I can just maybe factorize this. A times a square minus 2 is equal to 0. So therefore one solution is a is equal to 0, and as a consequence of that b is negative a. So b is equal to 0. C was a, so c is 0, and d was b, so d is 0. A can also be root 2 from this a square minus 2 is equal to 0. So b will be negative of that, c will be a, and d will be b, so d is negative root 2. Similarly, a can be negative root 2, b will be negative of that, c will be equal to a, and d will be equal to b. So we have effectively a comma c, b comma c comma d has 3 solutions. And yes, that's the end of the question. Okay, so moving on, we have some book suggestions to National Mathematical Olympiads, Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Sharagan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, so at the end we have a similar but challenging problem, and I wanted to solve a system of equations for all real numbers a, b, and c. Right, so a, b, and c are real numbers, and maybe just try this out in the system of equation. Maybe try to exploit the symmetry over here as well. And if you're able to solve it or make any progress on it, let me know in the comment section. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.